Right, let's get started, everyone. So you can tell us after if you like. All right. So in our notes book, everyone got their notes book. We're 1A, linear relationships. So today we're moving on from the background information on equations and lines, and we're starting linear relationships in the textbook, chapter 1A. Over the next few lessons, we'll work through chapter 1, and then we'll move into chapter 3. Where things will really start to pick up a little bit. So we have here, we've got a definition to begin with. We have two variables are linearly related if they are connected with a straight line. And then we have a special case called direct proportion. These variables are said to be in direct proportion if it goes through 0, 0. 0, 0 on the Cartesian plane, if this is a Cartesian plane, 0, 0 is just the point of origin. Okay, fill in the following table. So we have Mario is a plumber, he charges $70 per hour. Alright? Luigi, he has a $100 call out fee. So for him to rock up at your door, he's charging $100, but then he only charges $50 per hour. So we're going to fill in the following table. So firstly, we'll go for Mario. If you employ Mario for 0 hours, he's going to cost $0 because he charges $70 per hour. If you employ him for 1 hour, $70. For 2 hours, $140. Okay, for Luigi, if you employ him for 0 hours, he's going to charge you $100 just to arrive at your house. Okay? Which means if you employ him for 1 hour, you've got the $100 call-out fee plus then the $50 per hour. So he's going to be $150 for 1 hour and $200 for 2 hours, going up by 50 each time. So here we have two different plumbers and the different rates that they're going to charge. Now what we're going to do, we'll just start by plotting both of these on this graph here. On the axes here, I'm going to call this time in hours. That's my x-axis. And on the y-axis here, I'm going to have cost. Now remember in science, this is something that we'll keep hitting, but this is our dependent variable, right? The cost depends on how long they work for. All right, so that makes a lot of sense. And I might get another colour to get both of them going. Mario and Luigi. So, we'll plot the points for Mario. He's got 0, 0. That's the first point that he passes through. When time is 0, his cost is 0. For 1 hour, he charges $70. And for 2 hours, he's $140. So the path that Mario takes is going to look something like that. All right, hopefully it looks a bit better for you. All right, Luigi charges $100 just to rock up at your door, but then he's charging $50 per hour. So for 1 hour, we're at $150. For 2 hours, we're going to be at $200. So this is the line that Luigi takes. Okay. So we've got both of those graphs there, and we're talking about the table. All right. Part B, state the equation of the cost of each plumber. So the best way to think about this, there's a number of ways we can find the equation. But I think the best way to think about it is the equation of a line, right, is y equals mx plus c, isn't it? So we want to know the y-intercept and we want to know the slope of each line. Now what we have here is we have all of these coordinates. So for example, this coordinate here is 0, 0. This coordinate here is x is 1, y is 70. This coordinate here, x is 2, y is 140. So we have all of these coordinates for Mario, and so we can find the equation of a line using the processes we learned last lesson. So let's do that. To find the equation of a line, the first thing we need is the slope. Okay, so the slope is the change in y divided by the change in x. That's y2 take y1 on x2 take x1. So in this circumstance, we've got 3 coordinates, and it doesn't matter which ones we use. I'm going to in fact use these 2. So we have x1, y1 and x2, y2. So I'm going to have 70 take 0 on top of 1 take 0. We have a slope of 70. Now this is of course what we expect. This makes sense in the context of the problem. Mario charges $70 per hour. For each 1 hour we go across, the cost goes up 70. So we have, for each 1 hour that we go across, the cost goes up 70. Mario has a slope of 70. So the equation of Mario's line, I'm going to write Mario in red, is y equals 70x. So we've got mx, and then we would have plus c, right, where c is the y-intercept. But what is the y-intercept of Mario's line? 0. Okay, so we wouldn't even bother writing plus 0. We just write Mario's line is y equals 70x. Okay, for Luigi, all right, let's see if we can shortcut Luigi's line as well. So we could go through and identify these points. We've got 0 and 100, we've got 1 and 150, and we have 2 and 200. All of those coordinates are in our table here, so we can get them from our table, and we can find the slope that way. For Luigi, can anyone see what the slope is going to be? As 50. As x goes across 1, y goes up 50. Across 1, up 50. Across 1, up 50. The slope for Luigi is 50. Now you can, if you want to, if you can't see that, you can get it just using the slope formula from any of the coordinates that we have here. That's a perfectly suitable way of getting it. So we have for Luigi, we have 50x and then plus c, and his y-intercept is 100. Okay, that's where it crosses the y-axis. So we have 2 equations here that describe the cost for Mario and for Luigi. Alright, so that's part B. Which of the equations is directly proportional? So we'll recall that definition that we explored at the start of the lesson. They're both linear because they both lie in a straight line. The blue variable's in a straight line, the red variable's in a straight line. Which one's in direct proportion? The variables are said to be in direct proportion if it goes through 0, 0. Mario is the variable that goes through 0, 0. So our answer to part C, which equation is in direct proportion? Mario is in direct proportion. Okay, so direct proportion, that's just a special property of some lines if they pass through 0, 0. When x is 0, y is 0, it passes through the point of origin. Okay, part D. Find the point of intersection. Find where these lines meet one another. So there's 2 ways that we could look at doing this. One of them would be to just keep filling in this graph here and keep going and finding where they meet. If we're going to do it algebraically, what we want to know is we want to know, when does Mario's graph equal Luigi's graph? That's what we're trying to find. We're saying, when does Mario's graph equal Luigi's graph? Well, that's when 70x, the line 70x, is equal to the line 50x take 100. Okay, so we're going to equate these lines. And now we're going to solve this linear equation. We want to know when. We've got time on our x-axis. We've got the hours on our x-axis. We want to know how many hours until they intersect. We want to know, where do they intersect? So, if we're solving this equation for x, what we want to do is put all of the x's on one side and all of the numbers on the other side. So I've got 50x here by itself. Sorry, that should say plus 100, isn't it? Yep. I'm going to take away 50x from both sides. If I take 50x from both sides, 70x take 50x, that's going to give me 20x. And if I take it away from here, that's going to cancel. So we have 20x equals 100. We then divide both sides by 20. 100 divided by 20 will be 5. Okay, so the x value when these functions meet will be 5. All right, that's the x value. Now we are asked the point of intersection. All right, so point means it's like a coordinate. And so my graph here, I haven't sort of allowed enough room for it to occur, but they're going to intersect when the x value is 5. How might I find the y value when x is 5? Any ideas?
You put 0 and 5 on top.
We're going to put the 5 into which equation? It doesn't matter because these meet at that x value, which means the y value is the same and the x value is the same. We know the x value where they meet. So if I put it in here, 70 times 5, that's 350. If I put it in here, 50 times 5, 250 plus 100, 350. So the y value where they meet is 350. The x value is 5. Now, what this means, it says state the significance of it. Well, what it means is when time is 5 hours, before 5 hours, Mario is going to be cheaper. All right, Mario is going to be cheaper because he's charging. Let's even extend this out to show you rather than the graph. All right, and maybe I'll use my blue so you can see it better. 3, 4, 5, 6. Okay, Mario's going up by $70 each time, isn't he? 350, and then we'll have 420. Whereas if we look at Luigi, he's going up by 50 each time. Okay, so we can see from this table here, if we have a 5-hour job, Mario and Luigi cost the same amount. For jobs that are going to take 5 hours or less, all right, for jobs that are going to take less than 5 hours, Mario's cheaper. Look, 4 hours, Mario's only $280, Luigi's $300. For all of those values less than 5, Mario's cheaper. But if we go for a job longer than 5 hours, all of a sudden Mario becomes more expensive. This is because he has a larger slot. Okay, so I've explained that, but let's just find the point of intersection. Done. That intersects at 5 and 350. Explain the significance of this. All right, so I might just clear some room where our table was, and we'll just write something like for time less than 5, Mario cheaper. Mario is cheaper. And for time greater than 5, Luigi is cheaper. When time equals 5, they cost the same. Okay. So what we're doing in this exercise is we're making a connection between the linear equation skills and a real life context, okay? So like whether it be a plumber or a phone company or electricity, whatever it is, we've made that connection. I think the only new addition, the only new learning point is going to be that definition of direct proportion. It will pop up in the textbook questions. So let's spend half an hour going through exercise 1A in the